Good morning everyone. Today we will be discussing about the structural theory of organic chemistry, which comes under Unit 4 of the BSc program. Under this heading, today we will be discussing about the introduction of to organic chemistry, classification of organic compounds, types of covalent bonds, hybridization in single, double and triple bond formations, general properties and the nomenclature of carbon compounds. Now, let us look into the classification of chemical compounds. Classification depends mainly on the source or the origin of these compounds. Mainly these are divided into two types, it is organic and inorganic. Inorganic, everybody knows, you and I know very well that they are from mineral sources and they are obtained from the elements. Coming to organic compounds, previously people used to think that organic compounds could not be prepared in the laboratory, but they can be obtained from only from the living organisms such as animals and vegetables. So, for example, animal sources, you can have oils, fats, urea, etc. And from vegetable sources, we can get the examples of starch, sugars, gums, vinegar, spirit, indigo, perfumes, etc., etc. Now, as I said earlier, people thought, and mainly a scientist from Germany, Berzelius, he suggested that the organic compounds cannot be prepared in the laboratory. They can only be prepared by the living organisms. Why? Because the living organisms have some vital force in them or a mysterious force. This vital force is also called as the life force. Since the life systems, they contain such a mysterious force, they are able to prepare these organic compounds. So, therefore, they cannot be prepared in the laboratory. That was the theory proposed earlier, and the theory was well known as vital force theory. So, accordingly, organic compounds were defined as the compounds obtained from living organisms. Now, later on, accidentally, a scientist known as Wohler, Frederick Wohler, in 1828, he has prepared urea in the laboratory. Later on, scientists known as Hennel and Kolbe, they have prepared ethyl alcohol and acetic acid also in the laboratory. So, these preparations disapproved the vital force theory. Actually, Wohler accidentally he has mixed potassium cyanide plus ammonium sulfate, where he could get ammonium cyanate and potassium sulfate, which on heating urea was prepared. Therefore, this preparation has changed the purview of the organic chemistry and changed the definition of the organic chemistry. Now, the organic chemistry is defined as the chemistry of carbon compounds. After the proposition of this theory, another problem arose, that is, everybody knows that carbonates and carbon dioxide calcium carbonate, potassium carbonate, lithium carbonate, etc., are well known to be inorganic in nature. Therefore, they cannot be included under organic chemistry. Hence, again the definition has to be modified slightly, and again they have proposed that the chemistry of hydrocarbons is said to be the organic chemistry. Now, presently also the same definition holds good, that is, the chemistry of hydrocarbons is the organic chemistry, whether they are isolated from a plant or an animal or synthesized. What is making this carbon such a special one? Why this carbon has a special branch in the chemistry? Let us see. Why? Because carbon itself is special in nature. This has few special characteristics. What are these characteristics? Let us know. First and foremost is the carbon is tetravalent in nature. That is, every carbon contains 4 bonds around it. Second one is, it is able to form long chains and rings due to a special property known as catenation. This property of catenation makes the carbon very special in nature, and because of this, millions of carbon compounds are available today in nature. And the third one is, the compounds are generally covalent in nature. Covalent in the sense they are stable. That is another important point. And lastly, the carbon exhibits isomerism. So, these are the points, 4 points, which makes carbon very special in nature, and a special chemistry is being framed because of the numerous compound it is able to produce. Now, in order to understand and remember the properties of all these millions of compounds, we have to classify them in such a way that people can remember the characteristics of the compounds. Therefore, mainly these organic compounds are divided into two types. One is based upon the carbon skeleton, other based upon the functional groups, presence of the functional group. First, let us see about the classification based on the carbon skeleton. Now, the carbon compounds, depending upon the carbon skeleton, can be divided broadly into 2 types. One is the open chain and the other is closed chain. Open chains are also called as aliphatic compounds, and closed chains are also called as cyclic compounds. Open compounds are very simple, long chain like compounds. They are again of 3 types: compounds containing single bond, compounds containing double bonds, compounds containing triple bonds. Compounds having single bonds are known as alkanes, generally known as alkanes. Compounds containing double bonds are generally known as alkenes, and the compounds with the triple bonds are generally known as alkynes. Now, coming to closed chains or the cyclic compounds. These are again divided into 2 types. One is heterocyclic and the other is homocyclic. As the name implies, homocyclic compounds includes only carbons. The rings contain only carbon atoms. Such compounds are known as homocyclic. They are also known as carbocyclic. Coming to heterocyclics, as the name implies, in these rings other than carbon, elements such as nitrogen, sulfur, oxygen also will be present. Such compounds are referred as heterocyclic. Coming to homocyclic, again these are broadly divided into 2 types, that is alicyclic compounds or cycloaliphatic compounds. These are the compounds where you cannot find systematic way of arrangement of double and single bonds. Therefore, these are called as alicyclic or aliphatic compounds. Example is cyclohexane or cyclo-1-hexane. Such type of compounds are known as alicyclic compounds. Coming to arenes or aromatic compounds, the second type is the arenes aromatic compounds. Here the example is benzene, which is well known to each and everyone. All the arenes are found to be the derivatives of this benzene. For example, let us see the examples of this classification. Open chain looks like this. Open chain compounds, they can be straight chain or they can be branched chains or they can be complexly branched. In a straight chain, each carbon is in turn attached to 2 more carbons. In branched chain, each carbon is in turn attached to 3 more carbons or 4 more carbons. That is about the open chain compounds. Coming to cyclic compounds, I said earlier, they are again 2 types, homocyclic and heterocyclic. In homocyclic, alicyclic I said. So, these are the examples of alicyclic compounds. One is cyclopropane, cyclobutane, cyclopentane, cyclohexane, etc., where you cannot find such systematic arrangements of single and double bonds. Now, coming to aromatic compounds, these are the derivatives of benzene I said. So, this is benzene. All these compounds are known as aromatic compounds. What is the speciality of these aromatic compounds? Aromatic compounds have double and single bonds alternatively placed. Wherever you see, after each double bond, a single bond is coming. Again, double bond, single bond. Such a type of structure creates an aromatic system, and such compounds are known as aromatic compounds. Now, coming to heterocyclic compounds. Heterocyclics, as I said earlier, they contain other than carbon, atoms other than carbon, such as oxygen, nitrogen and sulfur also. For example, this is known as furan. Furan contains oxygen, a 5-membered ring, and a 6-membered ring is known as pyridine, where nitrogen is present along with carbons. So, these are few examples I wanted to show. Now, coming to the second type of classification, that is based upon the functional group. Now, we have studied about the carbon skeleton, based on the carbon skeleton. Now, we are coming to the classification based on the functional group. What is this functional group? Functional group is nothing but an atom or a group of atoms which decide the chemical properties of a compound. Such a group or an atom is known as a functional group. Now, all the organic compounds which contain a particular type of functional group show similar type of properties, and they are considered as a family or a class of compounds. For example, few examples are given here. You can see in the slide. Alkanes. If only single bonds are there, they are termed as alkanes. If a double bond is there, they are termed as alkenes. The functional group is said to be a double bond. If a functional group is triple bond, the compounds are said to be alkynes. And if a functional group is oxygen, they are called as ethers. And if the functional group is OH, a hydroxy group, it is said to be a hydroxy group, and the compounds are known as alcohols. Similarly, if a group CHO group is present, they are called as aldehydes. And if a group such as CO is present, they are called as ketones. And the family containing COOH group are referred as carboxylic acids. COOR refers to as ester functional group, and the compounds are known as, or the family is known as, ester family. Similarly, COOCO group is known as an anhydride group, and all the family, complete family is referred as an anhydride family. Similarly, NO2 is known as nitro functional group, and the compounds are known as nitro compounds. Likewise, ONO referred as nitrite, CONH2 is referred as an amide. Functional group is known as amide and the compounds are known as amides. Alkyl amides generally referred as. Then COX refers to acid halides, alkyl acid halides, and NH2 refers to primary amines. If NHR group is there, it is referred as a secondary amine, and NR2 refers to tertiary amine functional group and the compounds are known as tertiary amines. Then CN group is known as cyano group or a nitrile group. NC group is known as isocyanide or isonitrile and the compounds are known as alkyl isocyanides. Similarly, N2 group is known as azo group and the compounds are generally known as azobenzenes. Similarly, if an X group, X is nothing but halogens, X group is present, they are referred as halides. If a chloro group is there, they are referred as chlorides. If a bromine is there, they are referred as bromides, etc. And the compounds are known as alkyl halides. Then lastly, CH group. If a CH group is attached to the carbon, they are referred as thiols and or other name is mercaptan and they are referred as alkyl thiols or the starting member is known as methyl thiol. Now, we have got the idea about the classification of these organic compounds. Let us see about the bonds formed by the carbon atom. As I said earlier, carbon can form only covalent bonds, that too 4 bonds are being formed. Let us see in detail how this process goes. Now, as it is known to you all, the atomic number of carbon is 6 and the electronic configuration according to Aufbau rule and Hund's rule you have studied earlier in the intermediate also I believe. Therefore, these 6 electrons are being arranged according to the Aufbau as well as Hund's rule as this. The 2 electrons are placed in 1s level and 2 other electrons are placed in 2s level and the remaining 2 electrons are equally arranged in 2px1 and then 2py1 and the 2pz is 0. Now, total 6 electrons are being arranged here according to Hund's rule. We did not pair up here because following the Hund's rule they should be half filled first. So, therefore, this is the electronic configuration of the carbon atom in the ground state we say. Now, if you see this electronic configuration, here you can see only 2 half filled orbitals. So, from this we can get the idea that this carbon can take 2 more electrons from the outside, therefore forming 2 bonds, only 2 bonds. That means carbon should be a bivalent, but it is not true. If we see carbon, always carbon forms 4 bonds, always 4 bonds will be there around carbon. Therefore, this theory has to be changed. In order to explain 4 bonds in carbon, we have considered the excited state of carbon. Once the carbon goes to the excited state, then the electron in the 2s level jumps to the vacant 2pz level. Let us see that configuration now. Now, the 6 electrons, how they are arranged, please look into this diagram. So, 1s2 and 2s1, earlier 2 electrons were there here, one of this electron has jumped to the vacant 2pz here in the excited state. Therefore, now you can see 4 orbitals with a half filled, that is with a single electron. That means it is very much clear now that carbon forms 4 bonds. But another problem has arisen here. What is that problem? Here one orbital is of S type and the 3 others are of P type. Therefore, we can assume that among the 4 bonds of carbon, one bond should be of S type and the 3 bonds must be of P type. That means 2 types of bonds must be present in carbon. Again, which is not true. Carbon contains 4 bonds and the 4 bonds are identically, it is a practically proven. Therefore, it has to be something else. Therefore, a concept known as hybridization was introduced. What is this hybridization? We will see now. What is this hybridization? Hybridization is nothing but orbitals of different levels having similar energies combine or mix, forming new orbitals of identical energy and in the same number is known as hybridization. Once again, I will refer the phenomenon of combination of different orbitals having similar energies, not identical, similar energies forming new orbitals of identical energy in the same number is also produced, that is known as hybridization. Now you can explain the similar nature of the 4 bonds of carbon, the tetravalency of carbon, which we can see now in chemical reactions. Now you can explain from this hybridization. Just for the sake of clarity, I have given pictures over here. Here, just to see that one S is combining with Px, Py and Pz. So, various permutations and combinations are possible here. What are those permutations and combinations? One S can combine with one P forming Sp. One S orbital can combine with 2 P orbitals forming Sp2. Similarly, one S can combine with all the 3 P orbitals forming Sp3 hybridization. So, 3 types of hybridizations are possible here, that is Sp hybridization, Sp2 hybridization, Sp3 hybridization. Here in Sp hybridization, 2 are combining, producing 2 new orbitals having same energy and the remaining 2 P orbitals are unhybridized. They are left like that. Then coming to Sp2, 1s and 2 P's are combining, producing 3 new orbitals, 3 new Sp2 hybridized orbitals, 1 Pz is left unhybridized. And then the other one, the last one is the Sp3 I said, where 1 S and 3 P's are combining, total 4 are combining, producing 4 new hybridized orbitals having identical energy. All the 4 are having identical energy, and here no P orbital is left. All the P orbitals are being utilized in the hybridization. So, this is about the hybridization. I think you have got a clear idea now. Let us see about Sp3 hybridization first. What is it? In detail, we will get into the details of this hybridization. As I said earlier, 1s orbital of 2s level combines with 3 p orbitals of the second level, producing 4 new identical orbitals. The newly formed 4 orbitals are neither called as S or P. They doesn't have the characteristics of S or P, but they must be identified as every orbital, each and every orbital must be identified as sp3 only. Every orbital must be referred as sp3 type. Now, all these four newly formed orbitals, they are oriented in space towards the corners of a regular tetrahedron. For example, this is known as tetrahedron, where you can find 109 degrees of bond angle. Whichever bond you take, two bonds you take, you can have 109 degrees of bond angle. So, it is known as a regular tetrahedron. This is known as a regular tetrahedron. The four bonds occupy the corners of the regular tetrahedron. So, this is therefore, the hybridization is also referred as a tetrahedral hybridization. Yeah. Now, we have seen about the sp3 hybridization. I have shown the model sp3 hybridization being tetrahedral in nature. Now, let us take the example of the sp2 hybridization. Now, we have discussed about sp3, where I said as tetrahedral structure. Now, we will look into the sp2 hybridization, where I said one s and two p's are combining, producing three equal orbitals having identical energy. These are the three orbitals which are directing towards the corners of the triangle, equilateral triangle. 3. And planar in shape. All these three orbitals are planar in one plane. So, the sp2 hybridization produces a planar trigonal structure with one p orbital which is not participating in the hybridization. This is a purely pz having double dumbbell, above the plane one dumbbell and below the plane one dumbbell. So, this is about the sp2 hybridization. The sp2 hybridized carbon looks like this. sp hybridized molecule, where it is one s and one p are combining, producing two orbitals having identical energy. They are oriented or directed in a single line, this side one orbital and this side one sp orbital. This is one sp orbital and this is one sp orbital, and the two p orbitals are not participating in the hybridization. They are purely p orbitals having double dumbbell shapes. This is py orbital and this is pz orbital. So, they are left like this unhybridized. These are the sp2 orbitals. This is the sp hybridized carbon, which is linear in shape. So, sp is linear in shape and then sp2 is planar trigonal and sp3 is tetrahedral in shape. sp3 is tetrahedral. These are the three: sp3 tetrahedral, sp2 planar trigonal with one unhybridized p orbital, and this is sp hybridized orbital which is linear with the two unhybridized p orbitals. And you have understood what is organic chemistry and how it is classified and how many types of covalent bonds a carbon can form, and what is hybridization. And under hybridization, again we have seen sp3 hybridization, sp2 hybridization and sp hybridization, and remaining parts of this unit we will discuss in the next part.